Today we're going to talk about section 2.1, rational numbers and also absolute value. Before we begin, I want you to try to do these first two problems on your own. So I'll give you a minute. Go ahead and push the pause button to try those on your own. No cheating. We want to see if you remember what you learned in class yesterday. Now I trust that if you're still listening that you have already tried them on your own. Let's go ahead and check if you did them correctly. So we're going to pass out a negative 1/2 to 12p to negative 4r and to positive 8t. We're just taking half of each of these numbers. So half of 12 is 6. So negative 1/2 of 12 should be negative 6p. Half of 4 would be 2. So we get the 2r. And a negative times a negative makes this positive. Half of 8 would be 4, but since it's negative 1/2, that'd be negative 4t. And then bring that negative 3p down. We can only combine these, the negative 6p and the negative 3p, which gives us negative 9p. So we're really just getting a larger negative. Then the other two guys just come down, 2r minus 4, because they are not like terms. How'd you do? Did you do a good job? Let's check the next one. This one's a little tougher, 2/5. Now, this 7y, we won't do anything with it for now except bring it down. 2/5 times 10 over 1, 2/5 times negative 5 over 1. Now, I'll show the work on the side, but if we're doing 2/5 times 10 over 1, 5 goes into 10 2 times, and 2 times 2 is 4. And that's a positive times positive, so it stays positive. 2/5 times 5 over 1, 5 goes into 5 once, and all we're left with is 2 times 1, which is 2. Now that's a subtraction, so a positive times a negative is going to make that negative 2y. Then we can combine like terms. 7y minus 2y is 5y plus 4w. How did you do? Did you do a good job? Give yourself a smiley face. What'd you get, 2 out of 2? Excellent, 100%. Now let's move on to today's lesson. We're talking about rational numbers and how we categorize those. So back to your Cornell sheet, we're going to fill in, this is section 2.1, the definitions of the different categories of each of the numbers that we will talk about in algebra. Natural numbers are the positive whole numbers. And we use the letter n to represent the natural numbers. And I always say, naturally as a child, when I teach my 3-year-old, when I first taught her numbers, we started with the whole numbers, like 1, 2, 3, and so on. We did not start with the negatives, and we did not start with 0, because she couldn't quite understand what 0 meant. So think, naturally as a child, you start with these natural numbers. Then we add the whole numbers. Now this is where we get confusing. This is defined as positive whole numbers and 0. So now we just add the 0 to the beginning. 0, 1, 2, 3, dot, dot, dot. So next, when I taught my daughter numbers, the next number she learned was 0. We did not touch the negative numbers for a very long time, but we did add 0 so she could understand what 0 meant by then. And the whole numbers use the letter W. So far, so good. That makes sense. Naturals and wholes. Integers, this one is a little more confusing because they use the letter Z. We use I later on for irrational numbers, so we can't use I for integers. So they use Z instead for some reason. So integers, we just add another set, another category of numbers. So now it's positive and negative whole numbers and 0. So now we've got dot, 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 -2, -1, 0, 1, 2, dot, dot, dot. So we got all whole numbers, but now we include the negatives as well. So natural numbers are your positives, just positives. Whole numbers, your positives and your zero. And your integers, your positives, your zero, and your negatives. So we're just adding a couple more for each of those categories. Now, if we go down to the bottom of the page, we're going to draw a box. Now, the box represents all what we call the real numbers. And this year in algebra, we will only discuss real numbers. Now, within the real numbers, we break those down into two categories. And this is where the next two come from, rational and irrational. Now, the rational numbers, we use the letter Q. And again, we use R for real. So we have to use a different letter besides R, and they use Q for rational because a rational number can be written as a quotient or written as A over B as a quotient. So they chose Q because quotient begins with a Q. Okay? So when we divide up our real numbers, we've got our irrational numbers in this box, which we use the I for. And then we have this larger category. Well, it's not larger. It's just a separate category, which are the rational numbers. And we use Q for that. Now, rational numbers, when your mother says, you're being irrational, that means you're not making any sense, you're being crazy. So I like to say the rational numbers are the non-crazy decimals. Okay, the non-crazy decimals, or decimals that terminate, which means they end. So the terminator ends people's lives. That's why they call them the terminator. So if it's a terminating decimal, that means it has an end. Or if it repeats. So if it's a decimal that repeats, then that's also a rational number. So some examples. 0.25 can be written as a fraction, 1 over 4. It's also a terminating decimal because it has an end, it stops. Okay? 0.5 repeating can be written as a fraction. So any repeating number falls into this category. Any terminating decimal falls into this category. And a whole number can be written as a fraction, 5 over 1. So any whole numbers also fit into this category. So your rational numbers are your non-crazies, ending or repeating or whole numbers. The flip side of that are your irrational numbers, your crazy decimals. And I told you earlier that we use I for irrational. Crazy decimals don't terminate or end. So some examples. We're familiar with pi 3.14159 blah, 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 blah. That is an irrational number. When you take the square root of some numbers like 2, that will give you an irrational number, a decimal that doesn't have any repeating going on. The one that tricks people up sometimes is something that has a pattern but is not technically repeating. So 0.01, 001, 0001. You can see that there's a pattern, but that can't be written as a fraction. So that is considered still an irrational number. Okay? So let's go back to the notes. We're going to use these. Oops, let's finish something up here. So in the irrationals, these are the crazies. Crazy, 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 crazy. Within the rationals, then we can fit these other three categories. So think of them as boxes. The largest box would be this one, the ones that hold the positives, zeros, and the negatives. So that's going to be your integers, your positives, your zeros, and your negatives. These are all whole numbers in here. So the shaded region are your whole numbers. Within that, then we have a little smaller box that only includes the zero and the whole number, I'm sorry, the positive numbers, positive and the zero. So that's going to be your wholes. And then we've got a tinier box in there, the naturals, and that is only your positive numbers. So when you think about our next, what we do in our notes next, this box could help you categorize. If it's a natural number like 3 and it fits in the smallest box, then it automatically fits in the whole box, the integer box, and the rational box. Now notice the irrational and rational boxes are completely separate. You can't be crazy and uncrazy at the same time. Okay, no bipolar numbers here. You can't go back and forth. So if you're crazy, you stay crazy. If you're non-crazy, then you can fit out here. So like a fraction would fit out here. A decimal, 0.75, would fit out here. A repeating decimal, like 0.3, that would fit out here. And then your whole numbers can be put into these boxes inside. So let's look at our notes. We're going to keep that. You can keep that around to help you with the next portion of your notes. We'll slide that in right there. Okay. So examples. Name the set or sets of numbers to which each real number belongs. Now 5 was actually one of our examples. It's a whole number. And it's a positive number also. So because it's a positive whole number, we know it's a natural number. Now see where the natural box is? If it's inside the natural box, it automatically has to fit inside the whole box. It automatically has to fit inside the integer box. And it automatically has to fit inside the rational box. So if it fits in the smallest box, it fits in all of these. So that's going to be the easiest type, and it fits in all 4 of those categories. This one, number 2, would be easier to understand possibly if you simplify it first. -4. Now that's a negative number. It won't fit here in the naturals. It won't fit here in the wholes. But it is going to fit into the integers because it is a negative whole number. So z for integers. And then that box fits inside the rational box, so z and q. Radical 26. If we put that in our calculator, we get this number, 5.0990, and it keeps going, okay? No repeating, no terminating, because it keeps going. Therefore, it must be crazy, and that makes it an irrational. Cannot fit into any other box if it's irrational. However, when we take the square root of 36, we get 6, and 6, just like 5, is going to fit into the naturals, the wholes, the integers, and the rationals, all of them, because it's a positive whole number. It fits into all of those boxes there. Okay. Absolute value. We need to define that onto our Cornell sheet also before we get into this. So let's take a break for a second, move back to our Cornell sheet, which is right here. The absolute value of something is defined in junior high and in our book as the distance a number is from 0. So, for example, if this is 0, 5 is 5 units away. 5. So it has an absolute value of 5. So we write the absolute value of 5 equals 5. Now if we had -5, it's also 5 units away. So when we take the absolute value of -5, it's also equal to 5. So the distance, it is away from 0. It's always going to have to be positive because we can't move in a negative distance. Okay. You also need to understand that it is treated like a grouping symbol, like parentheses. So if you have things inside the absolute value, you must do those things first. And then, once you've simplified the whole inside of the absolute value, then and only then can you take the absolute value of it. So I'm going to give you an example in this bottom corner here. Move it over just a little bit more. So if we have 5 minus the absolute value of -8 plus 4, this, you have to complete what's inside here first. So we get 5 minus the absolute value, -8 plus 4 would give us -4, like that. Now you cannot get inside these walls. This is like a brick wall. So you can't take those two negative signs and make them happy or make them both positive. You have to take the absolute value of 4, and that's the only way you can get out of the walls here. The absolute value of -4 is 4 units away from 0, so that would be 4. And then we bring this negative sign down. 5 minus 4 gives us 1. So you must complete everything inside the absolute value before you take the absolute value of it, and then you can keep going. You cannot distribute into absolute value. You cannot fix two signs within the absolute value. Okay? And absolute value doesn't mean change everything to a positive. Okay? You do all the math until you're down to one number, and then you take the absolute value of that one number and you move on. So we're going to use that here when we're talking about absolute value. If you want to try these on your own, you can try these on your own first, and then fast forward to the end of the examples and see if you got them right. But for number 5, we need to begin by doing what's in here. 2 plus a -3. We're really subtracting them, which gives us 1. The 3 is large and in charge. He's the large guy, so we keep his sign, so that's -1. And keep the absolute value bars. Now you might need to be careful that you make your absolute value bars taller than your numbers, so you don't think that it says -111 or 1 minus 11. And then we bring the plus sign down, plus 7 down. The absolute value of -1 is 1, and 1 plus 7 is 8. Here, when we have a number kissing the absolute value bars, that'd be the same as if it were kissing a set of parentheses, except we have to remember to take absolute value. You can't distribute within the absolute value, but we know that in the end we're going to multiply by this too. So keep them out there for now. -8 minus 4, we have to simplify that. That's the same as -8 plus a -4, so we're really adding those and keeping that sign, which gives us -12. When we take the absolute value of -12, we get +12, and we have this 2. Now, you need to do one of two things. You either need to put parentheses around this 12 or put a multiplication symbol between these so that you remember you're actually multiplying these to get 24. So it is a grouping symbol. Once you finish what's on the inside, it's still a grouping symbol, which tells you in this case to multiply. So be very careful that you don't just write 212, or you don't think you're supposed to add those together. So I always, once I take the absolute value and I have something right outside, I use parentheses. That's just my, just what I do every time. Now here we have two sets of absolute values, so that means we need to complete this and complete this. 10 minus 3 is, of course, 7. Leave the absolute value bars around it. -3 plus 2 gives us -1, because we're really subtracting them for the same reason we did over here. And keep the sign of the larger number. Now, take the absolute value of each of these, 7. The absolute value of -1 is 1, and you need to bring the sign down. 7 minus 1 is 6. How'd you do? Good? Finally, we're going to write each set of numbers in order from least to greatest. And in order to do this, you will need a calculator, because we're going to have to convert these all to decimals before we can put them in order from least to greatest. So we take the square root of 5, and depending on your calculator, if you have one of these, you're going to push the 5 first, and then you push the square root button. Okay, and that gives us 2.236. Now, when you're doing this, I suggest you go to at least 2 decimals like money. So 2.23, $2.23. If you have one of these calculators, then you actually push the square root button first, which means you have to push the second and the x squared button, because there's a radical or a square root there, and then put the 5 inside, and then push equals. You get the same answer, of course, but you have to punch them in your calculator differently. The 2.36 is $2.36. You can leave that alone. And then 7 over 3, 7/3, you have to put that into your calculator, of course. The top number divided by the bottom number. 7 divided by 3, which is 2.33. So 2 decimal places, they're easier to compare and usually enough. So now think about money. What's the least amount of money? That would be this one, 2.23. So we write radical 5 as our smallest. Then $2.33 would be next, so we write 7/3 next. And $2.36 would be the last one. So when you're putting them in order, you can't use the decimals, you need to put the originals in order from least to greatest. Why don't you pause and see if you can do 9 and 10 on your own. All right, for number 9, we have to take the square root of 12, which is 3.46. Now that's going to make that negative. Now this one's tricky because of the negatives. This one is, of course, negative 3.48, and then when we take the square root of 11, we get negative 3.32. Now here's what you have to do with negatives. The negatives on the number line go in opposite order. So for the positives, 1, 2, 3 go in one order, left to right, smallest to largest. But for the negatives, they go in the opposite order. So what you need to do is think about which one appears to be the smallest based on not the negatives but just the numbers. So if you're thinking money, $3.32 seems to be the smallest, but since it's negative, that in fact will be your largest. So we're going to write that furthest to the right because that'll be our largest. The one, the medium one, of course, would be $3.46. So that one, negative radical 12, will go in the middle. And then the last one, negative 3.48, repeating, would be the smallest one. So think about what order you'd put them in if they were positive, and then flip the order. Okay? Negatives are in the opposite order. And finally, this last one, 0.43 repeating. Radical 6 divided by 5. Now, different ways you have to do this. If you have this calculator, you have to push 6, and then the radical button, and then divide that by 5. And that gives you 0.48. Well, if we round it correctly, that 9 after the 8 bumps that up to a 0.49. And then 3 divided by 7. 3 divided by 7, 0.43 if we round correctly. Now here's where we have a problem. We can tell the difference between this one, but if we write 0.43 here, it looks exactly the same size as that one. So it would be best in this case if we write this one to 3 decimal places, 0.429 if we round correctly, because that 5 is going to bump that 8 up to a 9. Now we can look at this from smallest to largest. The 0.429 will be the smallest, so 3/7 is your smallest. Then 0.43, repeating, will be your next largest. You're thinking money, $42 cents, or 42.9 cents, 49 cents, 43 cents. So 43 cents would come next, and 49 cents would be the largest, so that's radical 6 over 5. So go back and review those if you need any extra review. See how you did on those, and we'll see you in class tomorrow.